Okay, we're going to be looking at the next section, which is about pH, concentration scale for acids and bases. It's rather dark because I don't have the lights on, or many lights on here. Let's see. So our goals are to understand the pH scale and to calculate the pH of a solution from a concentration of hydronium ions in the solution, and to calculate the hydronium ion concentration in a solution from its pH. Let's take a look here. So pH, it's a scale for the acidity of aqueous solutions. And we have basically two formulas for pH. Here's one of them and here's the other. And I'll be honest with you, they're the same formula. They're just rearranged from one to the other. So pH is the negative log of the hydronium ion concentration. And recall that sometimes we use H plus instead of H3O plus. So we can say that pH is negative log of H plus. Now, one of the things that we may not know is that when you see those brackets, that means molarity. Okay, so it's built into the brackets. Now we can rearrange this formula. This formula basically says 10 to the pH. Well, actually, if we take the negative over here, 10 to the negative pH is equal to the hydronium ion concentration. So here we go. So these are the same formulas, just with a different emphasis. The emphasis here is on calculating the pH. The emphasis here is on calculating the hydronium ion concentration. Now the negative in this formula is so that when you change the hydronium ion concentration into a pH, you get a positive number. If we didn't have that negative, we'd get negative numbers for pH, and we're more comfortable having positive numbers for pH. So these are formulas that you want to memorize. Now let's look at the pH scale. If the hydronium ion concentration is 1 times 10 to the minus 1, and you use that formula where you have pH is negative log, and we're going to use 1 times 10 to the minus 1, and we're going to pretend that that's an exact concentration, although you can never have that. pH would end up being positive 1. And remember, we can rearrange this formula so it is negative pH is log of 1 times 10 to the minus 1. So the question here is 10 raised to what power, and that would be this, will get you 10 to the minus 1. Well, 10 to the minus 1 will get you 10 to the minus 1, and then you take the negative of minus 1 and you get positive 1. So you can see that when you have these numbers here where the hydronium ion concentration is 1 times 10 to some number, 1 exactly, the pH is simply the power of the 10, but the opposite sign, right? So instead of negative 1, it's positive 1. Instead of negative 2, it's positive 2. So forth and so on. Now, how do we understand these numbers? Well, if we take a look at these numbers, you can see that these numbers at top are larger than these numbers at the bottom. This number at top is 0.1 molar. This number here is 0.00000001 molar. It's clear that this number is much larger than that number here. So these numbers at the top have a higher hydronium ion concentration, therefore more acid. And here, these have a lower hydronium ion concentration and less acid. This is considered to be a neutral pH. Now, the thing that the book doesn't tell you is that we could look at the hydronium ion concentration in these aqueous solutions at the same time. We would find that the hydronium ion concentration here would be 1 times 10 to the minus 13. Here, it would be 1 times 10 to the minus 12. And what I want you to notice is that if you take the powers of 10 and add them together, they add up to negative 14. Negative 14. So here, you would have 1 times 10 to the minus 7. And look at those two concentrations. they're exactly the same. So you have the same concentration of hydronium ion as you do hydroxide ion. And we know that if you put those two together, they neutralize one another. Therefore, the pH at 7 is considered to be neutral. So we don't have this in the book, but I'm going to add it and let you understand why a pH of 7 is considered to be neutral. Now, if we look at this number here, we have 1 times 10 to the minus 6, because -6 and -8 total -14. And when you take a look at these two numbers, this number here that I'm pointing at and kind of wagging my finger at is a larger concentration than this one over here. So if we have more hydroxide than we have hydronium ion concentration, the solution is considered to be basic. And here, this would be 1 times 10 to the minus 5, and 1 times 10 to the minus 1. So down here we have a lot of hydroxide and very little hydronium. Here we have a little hydroxide and a lot of hydronium. So therefore, lower numbers on the pH scale mean more acidic. Higher numbers mean less acidic. It's kind of like the Winters scale. You know, the Winters scale is first is best. 1, more acidic. Okay, now, how do you round using logs? Basically, the number of significant figures in the molarity is equal to the number of digits after the decimal in the pH. So here, if the pH was 4.52 and we wanted to calculate the hydronium ion concentration, we have two numbers after the decimal in the pH. So this answer is allowed to have two significant figures, and we get 3.0 times 10 to the minus 5. Okay. Now, this is a kind of a hard thing to remember. You're just going to have to practice it. The number of digits after the decimal in the pH is equal to the number of zig figs in the hydronium ion concentration. Or another way to look at it is the number of zig figs in the molarity is equal to the number of digits after the decimal in the pH. Okay, so we're going to practice some problems now. Let's take a look at the pH of solutions. So lemon juice has a hydronium ion concentration of 0.0032 molarity. What is its pH? So pH is equal to negative log of the hydronium ion concentration. And what was that rule for rounding again? That the number of digits after the decimal in the pH equals to the significant figures here. So here we have 2 zig figs in the H3O plus. So we get 2 digits after the decimal in the pH. So here we can even estimate the answer if you wanted to. You can see that this number is greater than 0.001, which is 1 times 10 to the minus 3. And it's also less than 0.00 or 0.01, which would be a pH of 2. So the answer should be between 2 and 3. Probably closer to 3, I would imagine. All right, so let's take a look. Now on this calculator here, here are the buttons we want to push. To do the negative log, we're going to put negative first, and then log, and then we'll put 0.0032. And you don't need to put the end parentheses, but you can. I'm not going to do it. And I'm going to put equal. And you see we get 2.49. So that's a number between 2 and 3. So we get 2 point, and we get 2 digits after the decimal. So we're going to keep the 49, and since that's a 4 there, we're going to keep the 9 as is. So there's your answer for A. All right, let's take a look at B. Seawater has a pH of 8.0. What is the hydronium ion concentration? So for B, we're calculating the hydronium ion concentration, which is 10 to the minus pH. And here we have a pH is 8.07, so we have 2 two digits after the decimal in the pH, so you get 2 zig figs in the hydronium ion concentration. So here, this is kind of the reverse of what we've done above, but we're always looking at the number of digits after the decimal in the pH. Okay, so here, this is going to be 10 to the minus 8.07. And here's about the only time I use this key on the calculator. A lot of people call this the caret key. So this is perfect for when you have a number like this. On the exam, if you leave your answer like that, I will count it as being incorrect. Instead, here's what you want to do. 10 caret negative 8.07. And when we put enter, we get this. This is such a small number that I'm going to put this into scientific notation on my calculator. And I get 8.51 times 10 to the minus 9. Now, according to this, we get 2 zig figs in the answer, so 8.5 times 10 to the minus 9. And of course, this means molarity. Okay, so there's your answer to B. Now, let's take a look at C. So C asks you, a solution of nitric acid has a concentration of 0.0056 moles per liter. What is the pH of the solution? The first thing you need to understand for C is that nitric acid is a strong acid. So when you put this into solution, it completely ionizes. Now, it's not really complete. It's like if you had like a billion of these, one less than a billion would ionize and 1 out of a billion wouldn't. Actually, that's too few ionizing, or no, too many ionizing. So this ionizes almost completely. Okay, so that means if we had 10 of these, they would all ionize and you'd end up with 10 of these and 10 of these. If you had 100 of these, they would all ionize and you'd have 100 of these and 100 of these. You with me here? So what if these were concentrations instead? What if this was a 0.056 molar solution? All of this would ionize, and this would be 0.056 molar, and this would be 0.056 molar. Just like the numbers here would be the same because these completely ionize, over here, the concentration would be the same. So the reason we can do C is because it's a strong acid. If it were a weak acid, we wouldn't be able to do that, because if we had something like this, which ionizes incompletely, if we had 100 of these and we started off with 0 of each of these, and actually I'm going to start off with 100,000 of these, and we start off with 0 of each of these, when we reach equilibrium, we probably have 99,999 of these and 1 of these and 1 of these. So here, the number of H pluses does not equal the number of acetic acids that we started with. So if C were a weak acid, we wouldn't be able to do this. But because it's a strong acid, we can. So we could say that the H3O plus, remember, H plus and H3O plus are the same thing, is equal to 0.056 molar. So moles per liter can be written as molar. And I need another 0 in there, I see. Okay, so we want to calculate the pH. The pH is equal to the negative log of 0.0056. And here, notice in this we have 2 significant figures, so for the pH we're allowed 2 digits after the decimal. All right, so here I'm going to show you again how I would estimate this. 0.0056, 0.0010. Can you see how this number here, 5, 6, is larger than that one, but also how 0.0056 is less than 0.0100. Well, this would give me a pH of 2 because it's 1 times 10 to the minus 2. This would give me a pH of 3 because this is 1 times 10 to the minus 3. So that means that my pH should be between 2 and 3. And it looks like this is halfway between the two, so you'd expect, well, it's going to be right around 2.5. Turns out logarithmic is not a linear scale, so it's not going to be 2.5. Let's see what it turns out to be. So I'm going to do negative log 0.0056 end parentheses. I didn't do that last time. Now I'm going to put equals, and we get 2.25. And that is between 2 and 3, a lot closer to 2 than it is to 3, even though the concentration is halfway between. Again, because the logarithmic scale is not linear. Okay, so our answer is going to be 2.25, and we keep 2 digits after the decimal because this has 2 significant figures. Alrighty then. Put that to the side. And we're going to look at the next problem. Calculating and using pH. So we have that a table wine has a pH of 3.4. What is the hydronium ion concentration of the wine? Is it acidic or basic? So the hydronium ion concentration is negative log, is 10 to the negative pH. So we have 10 to the negative 3.40. And we're going to plug this into our calculator using the caret key. So 10 caret negative 3.4. And I get 3.98 times 10 to the minus 4. And here, this guy has 2 digits after the decimal, so I'm allowed 2 significant figures. So this becomes 4.0 times 10 to the minus 4, and that's molarity. So, is it acidic or basic? Remember, 7 is the cutoff for neutral. Anything lower is acidic, and anything strong or larger is basic. And since 3.4 is lower than 7, this is going to be acidic because 3.4 is less than 7. Okay, so there's the answer to that one. Now let's take a look at this next problem here. And I'm going to flip this around like this. What is the hydronium ion concentration of a 0.001 molar solution of nitric acid? And remember, this we can do because it's a strong acid. So we have the hydronium ion concentration will also be equal to 0.0013 molar because nitric acid is a strong acid. And it ionizes completely. I'm going to put completely ionizes. All right, what is its pH? The pH is negative log of 0.0013. And here, since we have 2 significant figures, we get 2 digits after the decimal. So I'm going to plug this into my calculator. Clear, negative log 0.0013. And I get 2.89 times 10 to the 0. Oh, I have it in scientific notation, that's why it's doing this. 10 to the 0 is the same as 1, so I'm going to cross that off. And the pH is 2.89, which makes it acidic. Okay, So, of course, it's acidic because it's a solution of nitric acid. All right, so I'm going to put that to the side. And we have one more problem here, calculating and using pH. So what we're supposed to do for each of these is we're supposed to calculate the hydronium ion concentration if given the pH and say whether the solution is acidic or basic, or if given the hydronium ion concentration, calculate the pH and say whether the solution is acidic or basic. So I have these written on another piece of paper here. And let's go ahead and address each of these issues. Now, right away, that's less than 7, so I know this is acidic. And this is greater than 7, so I know it's basic. I can actually do this with these numbers too, because remember, 1 times 10 to the minus 7 is neutral. And if it's a greater concentration, it's acidic. So this is acidic. And if it's a smaller concentration, it's basic. So that means I expect these numbers here to be, irrespectively, this one less than 7 and this one greater than 7. So to do this problem here, to get the hydronium ion concentration, we're going to do 10 to the negative pH. So here, that's going to be 10 to the minus 1. And so here, you have 2 digits after the decimal. So we're allowed 2 significant figures here. So we have 1.0 times 10 to the minus 1, and that's molarity. All right, now here we have 2 digits after the decimal, so we're allowed 2 significant figures. So we have H30 plus is 10 to the negative 10.5. So let's see what that gives us. 10 caret negative 10.5, and I get 3.16 times 10 to the minus 11, 2 zig figs, so 3.2 times 10 to the minus 11 molarity. Now, how do we do this one? We do that the pH is negative log of the hydronium ion concentration, so 1.3 times 10 to the minus 5. So when I plug that in, negative log 1.3 second EE negative 5 end parentheses, and I get 4.88. Now here, since I have 2 zig figs, I'm allowed 2 numbers after the decimal. So I'm going to put 4.89 because it's 4.886. Okay. So let's do the next one. We have the pH is negative log of 2.3 times 10 to the minus 8. Okay, so negative, clear, negative log 2.8 second EE negative 8. And we get 7.55. And here you can see that this is pretty close to 1 times 10 to the minus 7, so this is pretty close to being neutral. But it's just slightly above, so that makes the solution basic. Okay, and that's it for this part of the module. Thank you very much for listening.